And of course, yeah, feel free to share your thoughts about the workshop on Twitter via Naiades project using the hashtag Naiades webinars. Okay, I think that's all about the rules. And let's switch to the today's presenters. So my name is Matej Pusinkovic. I'm coming from JSI. I will be moderating this this webinar, and so the order the presenters are here listed is the order according the agenda, and our first presenter will be Julian. Julian has a PhD in the field of geotemporal data analysis and statistics. He is currently working at DISY as a research coordinator, mainly focused on spatial temporal big data. The second presenter will be Cédric. He's an engineer for industrial systems, specialized in embedded systems. Since June 2011, he has been involved in several European research projects concerning the Internet of Things, IPv6, home automation, and smart cities. Then we'll listen to Robin, our little bit mysterious man. So Robin, he has finished his studies. He's finishing his studies at the Applied University of Mannheim, and he specializes in spatial data names to further specialize in the analysis of time series and data analysis. And currently, he is working at DISY on data integration problems. Then we'll have a presentation from Wolfgang. He focuses on the application of statistical and machine learning methods to model microbial risks in various water systems. Specifically in the project Digital Water City, he developed prediction models to support bathing water quality management, which I think he'll be presenting today. And last not least, definitely, we have Katharina. She studied technical informatics, but later got into the environmental informatics, working on various topics pertaining to environmental data. In 2016, she founded DataCove EU, where she has been involved in various international projects working on modeling observational data, and she's the co-chair of the OGSO and the MSWG, and currently finalizing the new version of the ISO 90,156. Not sure if I understand what this is, but maybe this is related to your presentation, and I'm really eager to find out. In addition, she's a co-chair of the OGS Conceptual Modeling Group. Sorry, this is the second batch of our presenters. So the agenda is divided in three sessions. The first session will be about data models. Mostly, I expect more theoretical presentations, while the second session will be witnessing a more practical demos presentations, and after that we'll have a panel discussion and finally wrap up. Yeah, so according to the agenda, every presenter has about 15 minutes to present his topic. The first presenter is, as I've mentioned, Julian. Hello, Julian. Please turn your camera. I will make a presenter now. Okay, you're a presenter, and feel free to start whenever you ready.
So, then, thank you for your kind introduction. I'm happy to be here and have the first presentation. So for obvious reasons, since I have the first presentation, it's the most meta presentation and the least technical. So I'm hoping later for the future presentation, because I'm looking forward to more technical stuff. However, I want to make a short introduction about data models in general, data model validation, and a little bit also about the topic of the webinar, what is actually IoT technologies for smart water systems. So our key motivation, why do we do actually anything we talk about today, especially the motivation behind data model validation, is we want to enable and use the full power of IoT for the water sector. What do I mean by that? IoT, by its definition, which we go a little bit more on that later on, has highly heterogeneous data. It has a manifold of different data types, different input, many different sources, and each of them have their own reasoning. So for example, we can have data models of domain experts of the water area. Some are more for wastewater, which can be more particular. We can have stuff like from smart city areas, all the different things. And everything of those, what they gather is valid, and it's a good idea, but sometimes to get them put together is, let's put it mildly, challenging. And this, of course, will result that we get highly conflicting data, we get incompatible inputs, the need for expensive transformation. So for example, a typical example I do, which is actually the most simple case, we have sensors of different companies working together. Some companies have a different area values, some sensors measure something a little bit different. Sometimes when we have bigger companies, they use their own data models for some reason. And well, then we have to put them all together. And that's quite challenging. But we want to use this because this is interesting. This is data, this information we can use. And to ensure that we can utilize all of this information, all of these possibilities for the water sector within a reasonable effort, we need to use agreed upon open data model and validate those before we use them so that we can have a benefit. So this is actually, broadly speaking, the motivation why we are doing today's workshop and for I think most of the work we will be, or even all of the work we present here. So first, a very short introduction. Like I said, I have the meta part about IoT and the water sector. So please excuse my brevity since I only have 15 minutes. At its core, what is IoT? IoT is the so-called Internet of Things. The core idea behind it, so again, very condensed, is that everything we have is mapped to an online twin, and that every data we get can be gathered in real time, can be shared, can be put into some huge system, so we get all the information outside, which can be created, which is there, that it can be used. And well, this is the second point. This can then be analyzed even in real time. So not only do we get more information about the world than before, since everything is measured, everything can be mapped, but also we can analyze it and therefore use it. So for example, this can be done by AI. One of the more modern buzzwords is difficult when it's over 60 years old. We have stuff like complex event processing and even other methods for data analysis. Sometimes we can use automated analytic pipelines, so a lot of different stuff. For example, later we have to talk about the early warning system for bathing water quality, where we see one of those examples what we can do when we have IoT data. And well, one of the most common examples when we look into IoT are connected appliances, wearables, smart factories, tracked shipping, and smart city, but they are mainly traffic, noise, and pollution. So while this is all interesting, why do we need something in the water sector? And why do we need IoT in the water sector? Well, water is special. Since most of you here are from the water sector, I don't tell you anything new. Basically, since when we look at stuff like ship tracking, a lot of the smart factories, we only have sensors in some places. Perhaps we know if they are in some pipeline, but they have no concept of space or geography. They have rarely other concepts. So we have more than just online sensors, while they are still quite important. So we have later the talks about SensorThings API and see how important they are for this use case. In the water sector, we have much more data than just online sensors. Again, this is discredit to how important they are, but well, in the water sector, we have highly interconnected and interdependent data sources. So everything we do at one case or every measurement we get at one area can be connected to another thing or to another area, can be connected over time, and we need how they interact with each other. We need to know that. So we always have a relation to time and space. The typical thing we know is weather. Weather is different in a different area, can be changing over time. So perhaps at some of your locations where you're sitting now, it rains. At other, there will be sun. Most of the time it will be cold today, but well. So depending on where we are, we have different needs and different impact on the water. So when we look in the typical scientific examination or examples, the water consumption is a little bit higher when it's hotter outside, especially when it's over 30 degrees Celsius. And in winter, well, There I'm not a water expert, but even then we have different requirements on the water sector. And therefore, we need a lot of different data types apart from those measurements. So for example, we need areas, we need time series, we need spatial temporal data, since we have the time and the space together, and a lot of interaction. So we have here a small example of the Naiades project. The area, the graphic is provided by the UDGA, the UDGA Alliance, where we have the measurement of, or the need for watering of plants in the city of Ville-d'Agues. We have a sensor at each flower pot, so we know how much water is in there, how much water does each flower pot need. But we also have the weather of the whole city, the weather forecast of the future, how it rained in the past, how much we watered the water before. We have known, are there tree areas next to them, and then we can derive recommendations about when to water it, how to do it, can we have optimal routes for all things. So all this together, that's IoT for the water context. And this is just one very, very small example. And I think most of you, once you start thinking about it, will get way better examples than I can have. But you see, but as you can see, we need those different data types. We need those different data bases, different sensors, and all of this is special in the water context, which we don't have as much in other IoT contexts. So on we go to data models. Basically, what are data models? So why are we talking in this session about data models? Yes, I know Wikipedia is not the most scientific source, but sometimes it has very, very nice definitions and way better than we can sometimes formulate. And the data model is in its core an abstract model that organizes elements of data and standardizes how they relate to one another and to properties of real-world entities. So basically, this allows us to reflect the real world into the digital world and make it readable for machines, make it readable for humans, and to ensure that the data is in a set format and then we can trust this format. However, each data model fulfills the need of a certain domain. So there's never the perfect, correct data model, but there's a data model which is suitable for the context where it's needed. And this is where we go to the data model validation a little bit more. Data models at their core are fundamental tools for the harmonization of data. They enforce a set schema everyone adheres to, but at least in principle. So that means we know how the data is built upon. So we had before the example of different sensors of different companies. When they all have the same data model, then we know it's easier to use them because then we know how they are saved digitally, how they're ordered, and then we can just use them basically directly, or can build our analytical models in the exact same way as the data models are put into the system. And well, thereby they enable interoperability and global governance, which is quite nice. So we can reuse them, we can share them, and well, they're usable actually. Well, an example I sometimes do, or a short overview, where we have the problem where we don't have common data models a lot of the time in the smart city context. The smart city solutions, as well you all know, are becoming increasingly common, and they provide many, many benefits, in particular for municipal agencies. However, as of now, there are many competing solutions. So we have not only one smart city solution, but several big companies, small companies, EU projects, they all have competing solutions. And as it would be too easy otherwise, they have highly heterogeneous standards and data formats. So every solution has their own formats, which works perfectly within the solutions, but not so much for the exchange of data to another solution. There is no agreed upon the exchange format, because once you're in a system, they don't want to let you out. So they can keep you as a paying customer. And a lot of the key hardware providers, especially the big ones, provide only their own proprietary and closed solutions. So this is the problem when we don't have those data models. And this leads to a vendor lock-in, as we know, for example, also from cloud computing, and a lot of missing innovation, especially for SMEs, which can't then compete or be included in this data space. And this we don't want to do for obvious reason. In Naiades, a very short introduction to our data model approach, we chose the existing FIWARE data models, or the NGSI data models to be more precise. Why do we use this? Because FIWARE is a standard proposed by the European Union and many existing research projects, and also for the FIWARE Foundation. So it's a big standard used by many companies, and it's especially nice for SMEs and research agencies. So it is used, and it can be used by a lot of parties, and a lot of parties can trust it. What is also quite nice is the FIWARE data models are based on the JSON standard. So it's a very open standard. It's a very simple human readable standard. Most of us can use it or can read it and can easily adapt it, even if we don't have as much technical knowledge as some other people. So we don't need a computer science degree to actually read and adapt JSON, which is quite nice. They have a lot of extensions in JSON. So for example, GeoJSON, if we want to include geographical data, JSON LD, if we want to use the so-called linked data, or semantic data annotation. And well, as I said, JSON is human readable. Here on the right, we have a simple example of such a data model. We have an ID, which is saved as a text, so it's a normal written text. And we can also have something like a location, which is a type of location, or the width of something, which is based on a number. So we can easily read and see, when I want to include this in this data type, or this in this measurement, how do I need to save it? And then I can easily use it later on. And this is quite nice. If you put it forward, so for example, in the city of Garouche, Ville de Garouche, we used several different data models for different use cases. So for example, if we want to look before at the fountains or the plant boxes, and we see, okay, when we want to use our plant boxes, we have several different plant boxes. Each of those has then a data model called flower bed, which saves all of the key information we have for our flower bed, which we are using, and also has a humidity sensor, which is then saved in a data model device. And this we can then build for every single use case for different things. Look, what data model do we need? How do we need it? And what can be used for which kind? And since we have several different data models, we can represent everything we need, which is quite nice. So now to put it all together, it's the data validation. So why do we need this actually? Why do I talk about all of this? Basically, any processing of data we have is built upon these pre-existing assumptions about the incoming data. First, that we know that the structure and the content is correct. Since we have our data models, we can assume that that everything we get is based on those data models and the structures in the exact same way, and the values are of a certain format. But well, reality is not as nice as theory for some reason. Therefore, the data can deviate from this assumption. So for example, we can have data corruption during the communication of data. We can have some simple programming errors. We can have new sensors which are not compatible with the data models or not yet transformed. So all of these things can happen without any malice, just because it happens in reality. And to ensure that all these assumptions we have are fulfilled, the data has to be validated. That means we have to check every time, is this exactly the same as the data model? Is this allowed in the data model, or is this wrong? And well, there are two basic approaches, how to or where to validate these models. We can do this either at any time in the system, any time the data is consumed. So for example, every time a new AI model, analytical model, whatever, is used, then it can check, is the data model correct, and then use it. This is quite nice, because then we need only to check the data models we then use in the data in the analytical model, and can be quite nice localized. However, it's quite expensive, because in every time we use a new analytical model, we have to check it again. So it takes quite some effort. The other approach is to validate it centrally and then trust the data from that point on. So every time data enters a system, we check it. And after that, we say, okay, once it's validated or checked and it's validated, we trust the data for the future, so that we only have to implement it once, which is quite nice. This is actually the way we are doing it in Naiades, and we'll present it later on. And finally, we have also the challenge how to deal with changing data models, because data models can change over time. Sometimes we have new needs, we have new sensors, new possibilities, and the local models have some problems. Very simple here in the Naiades way. How do we do this? On the left side, we see all the different data sets we can get in the system. This is then sent to the Naiades platform, where we have one central storage area. This is called the historical database and our Orion context broker. And every time a new data set comes into the system, it gets to our data model validation tool, which looks up all the data models, which we save centrally, and can they adapt. And if they are fine, they will send by the context broker or directly to the historical database. And if not, they are rejected. And we check this for every new data which comes in, also for the entailment data. With that, I'm just in time. Sorry for the little overtime. Thank you for your interest, and I'm looking forward to all the other more technical talks. And thank you. And now I have to just see there.
Thank you, Julian. Thank you for this presentation. I have a few questions, but I will save them for the panel discussion. Now we are. Let me welcome Cédric Crettaz. He will be presenting the integration into the FIWARE. So from a more generic data model presentation to a more specific open standards. So Cédric, please, the floor is yours. Let me just make you a presenter before that.
Thank you very much.
Okay, make a presenter. Okay. Okay, and you're set.
Yes, you see my screen now?
Yes, yes, I can see.
So, welcome everybody. I will present you some basic elements of to integrate the data coming from smart water sector into FIWARE. So, the objectives, what UDGA has done during the Naiades project is to integrate water data into FIWARE from multiple sources of water data. Firstly, we have IoT sensors. A sensor is basically measuring a physical parameter or several physical parameters in the environment, so the temperature, soil moisture, chemical components also in the water, which is very important. We have also several data sets coming from SCADA systems. A SCADA system is basically a system permitting to monitor and control a process, a technological process, typically in the context of water management. The water quality can be monitored by SCADA system and to put automatically some chemical component in the water, typically chlorate and something like this. We have also different data sets coming from different databases across Europe. Basically, we have 3 pilots in Naiades. So we have a lot of data coming from these 3 pilots, and also open data repositories, in particular in the context of smart water, weather and water history. We can typically use to do some machine learning, for example. Basically, it's what we have as inputs in Naiades. So the steps for the integration are not so many, in fact. The first one is to install the Naiades IoT platform, select a data model, create an entity in the IoT platform, create a subscription to store the historical data, update the attributes of an entity. So an entity is a virtual representation of a physical equipment, a device, a forward bed, like explained by Julian before, and finally get all the historical data to be used by a service or an application. The installation of the platform is quite easy. In fact, Naiades IoT platform is based on Docker, so we have several Docker containers, which limiting the numbers of dependencies to Git, Docker, and Docker Compose. So it's quite easy to install in a Linux virtual machine, typically, or on a computer. The steps for the installation are quite easy. You need to go to the Git from the project. We need to do a Docker Compose upd to create the minimal environment. We can check if the IoT platform is running well with Docker PS, and finally we can install other modules or services based on the instruction provided on GitLab. And you have something up and running, and you can start to work to integrate your data into FIWARE. So the second step is the selection of a data model. It's dependent on the data sources, of course. If we have something linked to water quality, we need to use the water quality observed data model. It's obvious. There are several possibilities. We have specific data models like Weather Observe, which represent the physical measurement available in the real world. Basically, typically the temperature, air temperature, is typically in this data model. We have also generic data models like device, which represent any kind of device. In your context of smart water in Naiades, it is a sensor. Can be a water flow sensor or a sensor measuring the soil moisture. There is different parameters which can be used to define which is the right data model. Data usage by the consumers of data. It is dependent of the application or services which are running at the end. The heterogeneous data sets, it means if you have different kind of data in the same data set, it could be useful to have something more generic like device. Single or multiple measurements at the same time. Of course, we try to send as much as possible a set of data in a short time, but with a large amount of data. It is particularly true with database. We have also take into account the level of complexity and flexibility brought by the data model. It's very dependent of the situation and the use case, in fact. Then we have a second step is basically the first step in the technical way to send data to the FIWARE platform. In your case, your Naiades IoT platform, we need to create an entity. So an entity is an instantiation of a data model for FIWARE. So we can do a HTTP post request to the context broker. The context broker is a generic handler from FIWARE, which is storing all the live data coming from different data sources, typically in your case from a soil moisture sensor in this example. So we need to do a post to the Orion context broker. We have a content type which is application JSON, and we can put a FIWARE service which in a certain manner define which is the pilot or the organization responsible of the data. In your case, Carouge, which is one of the 3 pilots of Naiades project. And we can define the ID, the unique identifier of the entity. For example, here we have a device data model with an entity, a name device test. And we have the different value and property like temperature and soil moisture, and also the location. The second step is the creation of subscription. Basically, a subscription permits to receive a notification when one attribute or several attributes of an entity is changed. Typically, Orion Context Broker is receiving a lot of data from different data sources, and then one of an attribute of a particular entity is changed. A notification permits to save the data from Orion Context Broker to the historical database. Basically, a new data means the previous data should be stored in the historic database, which is quite obvious if you want to have the whole history of all of your data. So to do this, you should do a HTTP post request to the subscription endpoint, which is a context broker. Basically, it's an endpoint with subscriptions at the end of the URL. And we can add a description. Basically, here we have notify quantum leap which is the historical API in the IoT platform. And we can here see what the type of entity which are concerned by the subscription is flower bed. And in the notification field in JSON, you can have the URL to the notification endpoint, which is the ContourNIP API for the historical database. And we can also mention which in this case, we are storing all the attributes when one attribute is changing. Then, as explained before, we need also to update an entity. Updating an entity is basically an update of one of the value of an attribute. So an attribute is typically a measurement. For example, in this example, we have the dew point, which is a number, and then the dew point is changed. The value of the dew point is changed. We can do an update from the source of data, and automatically we will update the context-oriented broker with a patch request. So it means in the URL you have the endpoint, which is the entity name. So in this case, it is a weather observed entity. And we can also have different updates in the same request. Basically, you can imagine to have the point here, but also temperature is the same time. We are supporting multiple updates on only one request by endpoint, so by entity. Finally, we can get the historical data from the ContourNIP API. Here we have a quick example with the URL. Basically, in this example, we are using an entity from the device data model. The name of the entity is device test, and we can retrieve directly the value with value parameters at the end of the URL, and we get the historical values from the device test entity. For example, here we have several values, two values which are stored in the same time with different values in function of the time. Final remarks. The slides are showcasing, in fact, what it is already implemented by the data collection and aggregation in Alicante, Varela, and Carouge. The Naiades IoT platform is supporting two versions of NGSI, NGSI version 2 and NGSI LD. NGSI LD has big advantages compared to NGSI version 2 is the fact we are supporting semantic interoperability, and we have more features concerning, of course, not only this aspect of semantic interoperability, but also tagging and other new features which are currently developed by the FIWARE community. And we can use the IT platform also with other FIWARE components for other IoT verticals, typically smart city, smart grid. Basically, it's not only a smart water platform, but we can integrate other IoT elements inside the IoT platform. You can find more information on GitLab. We have a dedicated big GitLab project for Naiades IoT platform, a wiki with a lot of documentation of to handle to push data to the IoT platform, and of course you have the website. And thank you very much.
Thank you, Cédric. Thank you for presenting your experience, how the integration to the FIWARE went within the Naiades project. Now the next presenter is Robin Knapp. Robin will be presenting inspections of data models. Probably that was already a little bit covered by Julian, but I guess Robin will be extending Julian's thoughts into more concrete examples. Well, we'll see. Robin, let me make you presenter. Okay, and okay, you are set.
Okay, so everyone should see my screen now. Welcome from my side, and thank you for the kind introduction. Actually, yes, I'm going to extend a bit on Julian's thoughts of the project, and what I'm going to do is I'm going to show you how we are actually implementing the data model validation. And for this, I made a quick schedule. I'm going to show you a little overview. First, I'm going to talk about how we actually model the data models. Then I'm going to explain what the data model validation means. For this, I'm using the master files, which you will get to know real quick. Then I'm showing an example, and at the end I will give you a brief overview of our architecture and how we integrate it into the Naiades platform. But at first, we can take a look at what I think is generally known as an IoT pipeline, where on the left-hand side you can see we do have a few entities that are home to the system. This ranges from the sensors to the actual data lakes where the sensor data is stored. And of course, in every IoT use case, we are wanting to analyze data, and we want to have an insight. So for example, with the water, we want to monitor water quality. We just not want to collect data and look at it. For this, I'm going to present I think it's also generally known as the data lifecycle, which starts with the creation of the data and the storage. And actually, this is the part where the data model validation comes in. And this is also part as a transition from different sensors, from analog and digital streams and values, where they have to be gathered, where they have to be sorted into models, so that we can, or so that more stakeholders can discuss about it and can analyze the data. We've also talked about it. A data model is used to ensure that everybody or every stakeholder knows how to talk about the same thing, and that we can exchange data and we can basically use it over time, and we can adapt it, we can change it. But the model is also used to have a central common understanding. And for this, in the Naiades project, there were discussions with the project partners, with the different use case hosts. What data do we need to describe their problems or their pain points? And we've already talked about this. There was a question, for example, how is something measured? What should be measured, and what attributes do we actually need to get from the sensors to describe a different a use case? And this does have some different aspects. For example, you might have the spatial aspect, as Julian talked about it. You have a location to it. You do have maybe some consumption, and you also do have a timestamp. So this event appears at a specific point in time. And that's what we want to store. And our goal of the validation should be that once we are storing the data, we can ensure, okay, this is correct. We can, everything that relies on the data lake is having, can make sure that the data is valid. And for this, we are, in context of the Naiades project, we are only performing a formal check. So we cannot say if a sensor measured something realistic. So this is not what we are going to measure. So it is only a formal check that we are implementing. And also our goal was to cope with different model versions, because I think you've already heard it, that FIWARE has different versions. We are using the NGSI v2 and the NGSI LD version. And actually the NGSI v2 version does have another version to it, let's say. So we have basically our data model validation has to cope with 3 different versions. And for this, we wanted to create a single point of truth that we can share across all stakeholders, across all developers, so they know how a data model have to look. And we are going to define master files for this. This was a approach that we came up with in order to create a single point of truth. And I'm going to show you the master files later. Also, this is also what Julian stressed out, is that we are having a central pipeline element, so that at one point we check the data and we don't have to check it over and over again in the processing. So it is, in this case, like I said, we are checking the models before we store them, but the data model validation could be used in any stage of the life cycle. So in another context, maybe we want to change actually when to validate. We can easily do this because the validation itself can be done at any project stage. Okay, now for the more practical part, I think I'm going to show and try to explain how the master files work, because you've heard about them and it might seem a bit loose at the moment, what they are doing and how to define them. Actually, how to define them we will discuss later, but for now I'm going to show you the concept. So we do have a model X. For example, you've heard about the flower bed model that is used in the city of Carouge. And we do have 3 versions. And in the first step, we want to make sure, okay, we can convert all these 3 versions into one version. And that's why we use a so-called blueprint. And each version has a blueprint for each model. And through the blueprint, we can create a minimum viable model. So how can we understand it? It's basically, let's say the model X of version A is an abstraction of actually the minimum viable model of X. So it is possible to create a process to convert the version A model X into the minimum viable model X by defining a few steps and by checking also a few formal things, and then having a model which in the next step we can then validate. And for the validation step, we designed the so-called specification models, which are also JSON. So that means they are human readable, which is, I think it's a good design. And we can then use the minimum viable model to check against the specs model. So even if Naiades or any other project wants to use this component and we are having another version, we can just create another blueprint for all the models and we are still fine. Let's see how this works with an example. I chose the weather forecast example model that we are having in the Naiades project. And I used the version 2 of the NGSI. And we can see here that on the left-hand side, you can see the model. On the right-hand side, you can see the blueprint. And on the left-hand side, you can see that it was common sense to use a date issued as attribute to describe the weather forecast, and a maximum attribute and a location attribute. So the date issued attribute is given as a datetime object, and it's dated to the 29th March 2021. And what it does on the right-hand side, because on the right-hand side on the blueprint, you can see we do have a date issued attribute as well. It does make sure that whenever the model weather forecast says, okay, I'm sending the date issued, and it says, okay, it is type date issued, then we as developers would define the attribute type in the blueprint to be datetime as well. So this is for the integrity of the data that is used in the platform. And for now, we can ignore the nav attribute in the blueprint and the metadata as well. So what we are then going to do is we are transforming the NGSI v2 version into the key value version. We call it key value, but it's actually NGSI v2 key value. And on the right-hand side, you can see the model that we are creating by using the blueprints. And this process is completely automated. So just by describing things in the blueprint, which I'm going to show in the next session or in my next session, we can then create the simple version. And on the right-hand side now of my screen, you can see the specs for weather forecast. And the specs file is, as I said, it's also a JSON, so everyone can read it. And the model, the data model validation service will then proceed to check what is specified in the specs weather forecast. So, for example, here it says, okay, we are requiring the attributes ID, type, location, and date issued. And when we are looking on the left-hand side in the model that is sent to the platform, we are having these 4 attributes, which is good. We are also having day maximum, but from looking at the specs file, we can see that this is an optional attribute. We also see that, for example, the date issued should be a datetime. Okay, how can we know that it is actually datetime what was sent to the platform? The data model validation will try to create a datetime object, and the datetime object needs to comply to a few formats. For example, we are using UTC time. So in this case, it looks good, at least for the date issued attribute. Okay. Finally, I want to show a quick overview of the top-level architecture. This time on the bottom of the screen, you can see the data collectors or data aggregators. This might also be a automated service, or it might be someone sending data manually to the data model validation. It's the blue rectangle in the middle. And on top of the screen, you can see the data lake, which is actually the Orion context broker. And before sending data to the context broker, the data model validation will perform a signature check, which is the KSI signature. And it will talk to the specification repository. This is where the specs and the blueprint files are located. And right now, this is a GitLab repository that we are also using to manage the source code of the platform. And I think just on time, I can finish my presentation, and thank you for your attention.
Thank you, Robin. Let's give floor to our next presenter. The next presenter is Hylke van der Schaaf, presenting the observation measurement and the OG SensorThings API. So I have said that I'm not really familiar with OGC SensorThings API, but it seems like it's a kind of a competitor to FIWARE. So this it seems that the heat is rising now, and the two competitors here. Okay.
They've got a slightly different focus.
Excellent. I'm eager to hear about it. The floor is yours.
You can give me share rights.
Make presenter. Okay, you are presenter now. The floor is yours.
Okay. Does it work?
Yeah, I can see it.
Good. Let's see if I can get that taskbar to go away. Okay, we'll have to live with it. Yes, thank you for giving me this opportunity to give a slightly different perspective on observations and data models. The topic of my presentation will be the observations and measurements model. That's a combined standard by the OGC, Open Geospatial Consortium, and ISO. And the OGC SensorThings API, which is a standard that is based on the observations and measurements model. Now, I'm pretty sure you all know the standardization organization ISO, but you might not all know the Open Geospatial Consortium. So a short introduction to OGC. OGC is an international consortium of over 450 companies, government agencies, universities, and private individuals. And their goal is to geo-enable mainstream IT. So they make standards that have location components in them. Some well-known standards are, for instance, about maps, web map service. Others are, for instance, CityGML. They also have a standard called WaterML. I'm wondering if you looked at that in the project. And they're dealing with Earth observations. So they make standards. They also do conformance testing to see if implementations actually correctly follow the standard. So what does OGC have to do with observations? Well, observations are made somewhere. And this somewhere is a very important component if you want to do something sensible with your data. Observations are often made by sensors. And because of this, the OGC has the standard web enablement branch of standards that deal with how to exchange sensor data. This was started around 1990 by NASA when they started making lots of satellite images, which are of course observations, and they needed to exchange those and distribute those, and they needed standards for that. And since 2001, the NASA moved this standardization effort to OGC. And some of the standards coming out of this effort are, for instance, SensorML, which is a markup language for describing sensors, the observations and measurements model, and the SensorThings API. And all of these standards deal with sensor data and sensor metadata. So, observational metadata. Let's say we've got an observation here. We've got a smiley face. There's a color, yellow, and an expression, happy. But as with just these data, there's not much you can do with it. I mean, color yellow, is that the color, or is that his how brave he is? And happy, is that his mood, or is that the hour where he usually buys his drinks? So you need more than just numbers. For instance, you need observed property. What is actually being measured? Is that a color or an expression? Important is also how it was this measured. What method was used? SWOT comparison, or was it a spectral analysis, which might give different results and different accuracies. So there comes, for instance, the data quality. Is it how good is the measurement? How reliable? Of course, for one observation, that's not too problematic, but of course, at some point, you're going to have lots of observations. And then, yeah, things become tricky. Of course, in the end, most of it is tabular data, which you could store in a CSV file. But then again, you get those data quality, methodology, units of measurement, and you don't want to repeat those every time. So yeah, you need a better model for it. So that's where the observations and measurements model comes in. And why is metadata important? Well, in 1999, the NASA had hoped to have an orbiter around Mars, but instead of around Mars, the orbiter went into Mars. And why was that? That was because NASA uses SI units, but a subcontractor, Lockheed Martin, used imperial units. And the numbers coming out of those calculations were similar enough that nobody noticed. But the difference was big enough that instead of around Mars, the orbiter went into Mars, which was kind of an expensive mistake. So that's why the observation and measurements model was made, which is an abstract model. So it doesn't have an encoding, because whether something is put into JSON or XML doesn't have anything to do with the model. It's just the encoding for the model, and any model can be put into different encodings. So to actually use a model, you need an implementation, and one of those implementations for observations and measurements is the SensorThings API, which is a standard for exchanging sensor data and metadata. Not just current data, but also historic data. The default encoding is JSON in the SensorThings API. It's a RESTful service, and it bases the request on another standard, the OASIS OData standard, for being able to do URL patterns, query options, searching, and linking. It also supports ISO MQTT messaging for push notification. And the big thing about the SensorThings API that it is really easy to use and understand. You can discover all your data with just a browser. You can follow links by clicking around. But at the same time, it is very powerful, and you can do very advanced queries. So how does it work? The standard consists of two parts. One is the concrete data model, because the observations and measurements model is very abstract. So you need an actual concrete implementation of that model, which describes the entities and how they are linked. And then the second part is the URL patterns for queries. That is, how do I get to my data? How do I search data? How do I add data, modify, and delete data? So the data model the default model consists of 8 entities. Can you see my mouse? I hope so. On the right is the observation, which is of course what's the measurement values, more or less. And on the left is a thing, because we're talking Internet of Things here, so there's a thing that has a relation to the observation. Things have locations, so you can know where a thing is. Things can have historic locations. So if you have a thing that moves, you can track where it was in history. Then, of course, we're talking about observation. So there is a sensor that made the observation that has, for instance, the metadata that describes, for instance, the accuracy of the sensor, what type of sensor it is, things like that. Then, of course, important for observations is the observed property that describes what is being observed. Is that a temperature? Is that a humidity, or a water level, or the concentration of some pollutant? Then there are data streams. Data streams are basically time series. So data stream groups observations based off one observed property, one sensor, and one thing. And in the data stream is, for instance, the unit of measurement. So all the observations for a data stream have the same unit of measurement. And then there's the observation with all the metadata belonging to an observation. Of course, there's the result. That could be anything, could be a number, could be a string, could be a complex object. And then there are, for instance, 3 times, or actually potentially 5 times. The phenomenon time is when was this phenomenon there, when was this observation made. And that can be either a time instant or a time interval. Because if your observation is actually an average over a longer period, it's very important to know when did this period started and when this period ended. So just with one time instant, you can't do that. Then there's the result time, which is also for the water domain quite important, which is the time when the measurement became available. Because quite often, for instance, water quality measurements are actually the actual measurement is done in a laboratory. So someone takes his rowing boat, goes into the middle of the lake, takes a water sample. And that moment when he makes the water sample is the phenomenon time. Then he rows back and he puts his water sample in a little bottle, puts an address on it, ships it to the laboratory. There they do all sorts of analysis. And the time when this analysis becomes available is the result time, which can be quite different from the phenomenon time. Then there's a valid time, which is a time period, which is very useful for instance, predictions. If I make a weather prediction now, I might say, well, okay, this weather prediction that I now made is only valid for 2 hours, because in 2 hours I want to have made a new prediction. So that's where you can see, okay, is this observation of a future event, is that still valid, or should I look for a different one? And each observation has a feature of interest, which is in most cases simply the location where this observation was made, and that is becomes important when you have a thing that moves, for instance. Then it's nice to have a direct link between the location and observation and not have to search in the historic locations of your thing. But it's also possible that you have a remote sensing. And if your thing is a satellite, then the thing you're observing is usually not the satellite itself, but the Earth, an area on the Earth, which is not at the same location as the sensor in that case. So a little example from the water domain, the French Geological Survey, BRGM, they have the database, the French database for all water quality observations. And when they wanted to look into the SensorThings API, they sent us their database and with the question, does this work? So that was a database of 136 million observations across 18,000 measurement stations, with 1,800 observed properties. The water domain has many observed properties, all those chemical compounds, all different observed properties. And this database was Inspire aligned, and water samples were analyzed in the laboratory, and there were many results per sample. So here's a little image of France where all those stations were. So how does this apply to the data model? So the thing in this case was the environmental monitoring station, which has a point location. The sensor is a lab analysis. The observed property is some chemical compound like copper or methane or things, or some scary chemical name. Then we have a phenomenon time and a result time. Phenomenon time was when the sample was made. Result time when it came out of the laboratory. And of course, we have a water sample, which was in this case the feature of interest, so that you can have quickly look up the water sample and then see, okay, what different compounds were measured on this water sample. So the next part of the SensorThings API is getting to your data. It's the URL patterns are based on the OASIS OData standard. Why invent things yourself when others have already done it? So the base URL is always ends in the version number of the standard. The SensorThings API by now has 2 versions, 1.0 and 1.1, so that you know when you do a request what version of the standard you're using. You can, you've got the basic get, post, patch, put, delete to manipulate your data. And one of the important things with get is that you can also directly query relations of entities. So you can say, give me all things, but you can also say, give me the data streams belonging to this thing. Or you can say, give me the thing of the data stream of this certain observation. You can query all along the entire data model. And that's very useful. Then some more parameters for the data model or for the API. There's of course things like top and skip, which allows you to paginate. If you've got millions of observations and you do a request, you don't want to get back millions of observations. You just want to get the first 100. And then maybe you want a few more, or maybe you say, that's enough. You can of course count, so you know how many observations there are or entities there are in total. So you know if it's even if it's already hopeless to fetch all of them, and whether you might improve your query, or whether it's actually a manageable amount. You can of course sort your items, because getting observations in a random order is not very helpful. And then very important, you can use select to limit the properties you're getting back. So if you request things, you can say, okay, but I only need the name, I don't need all the metadata. Filtering is very important, of course, and here you can filter also across the entire data model. So you can actually say, give me all things that have observations for a certain observed property, so that you can directly, so that you can limit how much data you get back. And very cool is the expand feature. Like if you get your things, you can say, okay, give me things according to this filter. And also give me the data streams. And for those data streams, I also want the first observation. So that you can, if you have a map and you want to show, you know what you want to show on the map, you can do one query and get exactly the data you need for your map. So that was very shortly an introduction to observation and measurements model and the SensorThings API. Are there any questions? Or do we keep the questions for the panel?
Thank you, Hylke. Yeah, let's leave the questions for the panel discussion later. And I would like to welcome now Wolfgang Seis. Hello, Wolfgang. Are you here? Okay.
Yes, I am here. Hello.
Hello. Wolfgang will be presenting an early warning system for bathing water quality, which seems a little more concrete example of data model usage. At least this is what I'm expecting from the title. Okay, Wolfgang, the floor is yours.
Okay, thank you very much. Also for the invitation and the possibility to present some of the results from the project Digital Water City here in this webinar. So an early warning for bathing water quality management is the title of the presentation, and the background is actually that, wait a second, so I cannot switch between slides. Yeah. Okay, so is that the city of Paris is actually the location for the next Olympic Games in the year 2024. And one of the objectives of the city is that it should be possible to conduct some of the competitions in the river Seine at this time. And so what we are doing in the project Digital Water City is that we try to support this objective by trying to predict the bathing water quality at this particular site. A little bit to the background and the data we are coping with is, so on the left side, you see here the bathing area. So this is actually very close to the Eiffel Tower. Then you see the two main rivers of the city Paris, the Marne, which goes from east to west, and the Seine, which flows from north to south here. And along the two river banks, you see these little orange dots, which are actually the outlets of the sewer system. So for combined sewer overflows, for example, so potential sources of contamination. Then you see the light blue points, which are rainfall data and rainfall gauges. Then you see the two brown points here, which are two major wastewater treatment plants, which discharge into the river and whose discharge flows with the river in the direction of the potential bathing spot. And you see larger blue points, which actually is river flow data of the two rivers. So we have a lot of continuous pollution sources like the wastewater treatment plants, but also discontinuous sources of pollution like pollution caused by heavy rainfall from the sewer network. And the objective in our study is that we are able to predict in real time the water quality in terms of fecal indicator bacteria at the bathing area of interest. And the approach which we chose to take is that we actually develop a very user-friendly web application and open source software, which should also be available for any other sites, not only for Paris, which enables the user to use their local data to construct, train, and evaluate machine learning models for the specific purpose of bathing water quality prediction. So for the predictions of fecal indicator bacteria, which also takes into account some legislation aspects, which are not so important here, but also which enables the user to make it as easy as possible to implement a real-time prediction engine by an automated data transfer and prediction module. So what we developed so far is actually a graphical user interface, which you can use to manage all your different data sources and which also manages the different entities in the FIWARE Orion context broker. So as soon as you create one in the user interface, it is automatically created in the context broker. Also users and so on. Then we have a module where the user can create spatial variables to group some of the predictor variables. And we have a machine learning module where you can analyze the quality of your prediction model. And if you are content, or when you like the quality of the prediction model, then we also provide the means that a real-time transfer of data and predictions can make it easy as possible. And the first prototype is you can see under the under the link here. So I just want to show some examples. For example, here, this is an example for the spatial variable creator. So what you can do in this web application is that you, for example, if you want to use rainfall as a predictor variable in your machine learning model, then it's very likely that rainfall stations which are very close to each other, that those data are highly correlated. So you would want actually to group these variables into one predictor variables, and this is what you can do by drawing this kind of shapes and polygons in the graphical user interface. give it a name, and then later on configure your machine learning model, selecting the bathing spot for which you want to make the prediction, and also select the predictor variables which you want to use. And after you have configured a certain set of a certain machine learning model consisting of the bathing spot, the predictor variables, and the algorithms you want to use, you can evaluate the quality of your machine learning model also in the graphical user interface, and also have a look at the time series. Like you can say, okay, what would be the predictions of this model when I used it for past data, which you can see in the lower right side. Then on the upper left side, you see which polygons have been used to create the model, and also how well the model performs on the training and test set. And what you also see in the upper left one is there is a little lever which says show the URLs for data transfer, and it will actually give you the endpoints in the Orion context broker where the user can actually send a patch request in order to change the value of, for example, the rainfall sensor to make this real-time data transfer possible. So you can see the setup for Paris here, for example. So every time you create an entity, like a rainfall sensor, an additional entity is created here in the Orion context broker. And if you are the user, you can now actually publish new data in the NGSI v2 format to the Orion context broker. And the web application already automatically created a subscription. So every time there is a change of a specific entity, our web application will get this new data and store it in the historical database, which actually implements the observational data model, and I think it also implements the WaterML standard. So it's I know it's the observational data model, but I think they are the same. Maybe my pre-speaker can correct me on this. But also we are managing the access to the Orion context broker so that actually only the users which have created a certain entity are allowed to change the value of this particular entity. And for this, we use the FIWARE components Keyrock and the Wilma Pet Proxy server, which is an implementation of an OAuth2 authentication authorization system. So only specific users can change the values of measurement stations which they have created by themselves. So if for the specific case of Paris, this means that the database in Paris, which is called Eden for hydrological data, is the source where all the rain data and hydrological data come from. Then our colleagues from Syntev, they create a middleware which actually transforms those data into NGS IV2, which is published to the context broker. We get the new data, make new predictions, publish it again to the Orion context broker, our predictions. And there will be additional communication applications developed for Paris, which use our prediction to inform the local decision makers and the public about the predicted water quality. For this, we also use FIWARE data models. So we use the smart data models, which can be found in the respective GitHub repositories for the water quality observed, for the E. coli data at the bathing spot, water observed, for the river flow, and for the discharges from the wastewater treatment plant and the networks. The weather observed data model for the rain data. And then we also developed a new data model, like for the water quality predicted, where the ID refers to a specific prediction model. And then we predict the water quality in terms of percentiles, which is the way the European Bathing Water Directive actually manages bathing water quality. So the thresholds are formulated in terms of the 95th and 90th percentile, and we also transform it to some official classification, like in this case, for example, excellent. Yes, so what is it? What do we do next? So now we develop this first application in 2022. We have a real-time testing phase of this setup planned for Paris, but we also want to validate the machine learning module, which works well for Paris, also at various sites, various other sites, but also have different stakeholders use this application, because of course, what we might find easy to use might not be easy to use by everyone. So we are working on continuous improvement of this software so that everyone can use machine learning models and IoT to improve their bathing waters. Thank you.
Thank you, Wolfgang. Let me, so yeah, we have come to an end of session 1, which is, let's say it was more theoretically oriented, although we already made a little bit of transition to the session 2. Which will be more model presenting. So we'll be looking at the live demos. So the next presenter is Robin again, and he will be demonstrating adding new data models. Okay, Robin, hello again. Aristotelis, can you hear me? Okay, Robin, yeah, please continue.
Okay, I think everyone should see my screen right now, and I'm going to do a little live demo with the local data model validation that we prepared, and I'm going to do the demonstration first in case it takes a bit longer, and I also prepared a PowerPoint that we can take a look at after, but I want to do the demonstration first. So actually what I'm going to do is I'm going to start my local service, and in this use case I want to show you that it is actually possible to integrate new models just at any point of the service, as long as it has started. And for our purpose, I made up a model. I called it demo. It's probably not really realistic, but I'm going to show you what I created here. This could be one instance of the model. It is the NGSI V2 version, the NGSI V2 version, right? And I said, okay, we're going to need a category for this model. We're going to need start and end date time. We want to have a measurement. We don't know what we are going to measure, but we need a measurement at this point. I also want to show that we are having some kind of source that is related to this measurement. And I want to show you a location. And this example also provides every data type that we are currently supporting at the moment with the data model validation. Okay, so I started the server, and this is the Postman application. I don't know if some of you might be familiar with. We're going to send this request. And by looking at the response that we get from the service, it says, okay, some kind of error arose. And it says the specs model can be found in the data repository. That's actually what we would expect at this point, because we had just made up a model, right? We just came up across with this and we made some measurements and we created this JSON model, and now we want to send it to the context broker. So the next thing that you would do is you would go to the central data repository. As I said before, at the moment we are having this hosted at GitLab, which is very convenient because every stakeholder has access to it. And here there is a folder. It's called specs. And I created a little file. And we are using a quite strict name conventions for these files. And as you can see, I called it specs demo_.json. And right now the service can't find it because of the underscore. I can show you what I did here. I said, okay, for every model that is going to be sent to the context broker, we need at least 2 attributes. We need an ID and we need a type. So I said, okay, the ID will always be some kind of text, some kind of textual string. It doesn't matter actually what it says, but we need to have it. Then we need a type. For the FIWARE convention, the type of a demo model would always be demo. So we say, okay, this type text, but we have a fixed value in this case. We want to have a category. A category, you can always think of a value that is picked out of a range of values. So in computer context, we usually call it an enum, or some of you might know it as enum. So we can assign a few values, and those are all viable. And if it's not one of these values, then the data model the service would decline this request. We use the start and the end date time, and those are types of date time. We use a measurement. It has to be a number. It could be float. It could be integer. We also use a source. This is some kind of text that we want to relate to our measurement. And last but not least, we want to use a location. And all these types that you can see here are the ones that are actually used in the source code of the data model validation service. So what we're going to do first is we're going to edit. Okay. Now we're going to check. Same request. Okay. It says, okay, some kind of error. Internal occurred when accurate improvement model. Okay, fair enough. We talked about it before. When we are using the LD version or the V2 version, the service itself cannot validate this because we are having data that we can compress this further, right? We can compress this into the key value version. And so we are heading back to the repository in GitLab. We are going to the V2 blueprint. I prepared this as well, just to make this process a little bit faster. And in this case, you will see we are still having the attributes category, start time, and datetime measurement source location. Actually, we don't have to specify the ID and the type of the data model in this case, because they do not vary. They will not vary in the V2 version versus in the key value version. So this will automatically be transferred to the key value model. As well here, in this case, we are giving not the exact same thing that we saw in the specification model, but we are more oriented. We are using the name here that is actually used in the V2 version, and this ensures that when we transfer the category from the version 2 to the key value, that we can actually check if it is a structured value. Okay, let's commit this. So we set up the specifications file, we set up the blueprints, and now this should work. Okay, looks like we are having a little error, but actually it's fine, because can show you here. We completed the validation successfully, which is perfect. What happens here is that the service will try to forward it, but I blocked the address. So that is what we would expect. And now I'm going to show you also a small presentation. And to sum this up again, I want to present to you the available data types that we already saw, how we can create the specification model, the blueprint model, and how the integration works. And I think it's a bit better this way. So you already saw the example, and I think now you can follow along a bit easier. And those are the FIWARE data types that we are currently implementing. So there are more data types that you can think of, but those are the ones that we are using currently. So this is also very extensible, so it is quite easy to implement new data types. And as I said, it was not the goal to implement every data type that FIWARE or any other context broker could use, but we wanted to use those that are really necessary for the use cases.
Sorry, Robin, you have the wrong screen share at the moment. We see the,
sorry.
No, it goes to the next slide. Now it works.
Oh, okay, that's the wrong screen. Give me a second. Sorry. So this should be correct. Okay, let's continue. Okay, I think this question we already answered. What data is necessary to characterize a use case? I think in the case of the demo model, we saw that it was just some timestamps. We used some location. We also used the measurement and some textual to describe our model and which attributes are sufficient to describe it. I think we've discussed this as well. This was also subject to this discussion in the Naiades project. And I think you're familiar with this one. And I'm going to explain a bit more what we have to, if you wanted to do this yourself. For every specs file that you are going to create, you need to add the required attribute, and you don't have to add the add and the type, the ID and the type, but it is recommended on a FIWARE site. You might wonder, is it necessary to put this in capital letters, or is it okay if I start with a capital letter? That's fine. So there is no restriction, and that is managed by the service. And I'm going to show you now how, or I can explain a bit further on the blueprints and how they work, because that's what you might wonder. Okay, I was talking about that this is optimized by the solvers, but how does it actually work? And I think I'm going to do the LD version, which I did not show you in the use case or in the live demo, but this one is quite clear. The nav attribute in the blueprint dictates what should be performed. So in this case, we want to compare the type that is given in the model, in the category attribute, with the type that is given here in the blueprint, which is property. And this applies to all the others as well. And we also want to perform an assignment, and we want to assign the value that is given by the category to the value that is used in the key value version, or the minimum viable version that we are going to create out of this blueprint. The same thing applies for the V2 blueprint, but the V2 version uses the metadata as well. And in this case, we want to compare the metadata with the metadata as well. So it is possible to specify some metadata here, but it is recommended to leave it, say, as a wildcard empty here, so that any metadata would be suitable. And as you can see here, we are comparing the attribute type enum to the actual type of the V2 version. When is it possible to add new models? I think that's already clear. We have to start the service. The service then takes a couple seconds to set up, and will then start to accepting requests. And I think that's basically what we did. When I started the presentation, the service was already running and the setup was already completed. So at any point, you could just go ahead and do the integration like I showed you. Just upload any specs file, upload the blueprints that are needed, upload them to the correct branch. I think that's a rather technical detail, but you have to upload it to the right specification repository, and then you're good to go. You can send your requests, and the data model will, the validation service will then continue to validate the models for you. As I said, I think it was a bit more clever to start with the live demo, so you know what was going on. And in this case, my presentation is actually finished. So I want to thank you again And if you have any open questions, just let me know.
Okay, thank you, Robin. The next presenter is Cédric, and he will be presenting the Testrun. Cédric, can you turn on the camera so I can find you easy? Yeah, okay, I see you.
Yeah, I will do a short demonstration because we are almost running off of time. You see my screen. Basically, I will present what we did for the Carouge pilot. Hope to use concretely the data model validation in a pilot. Typically, we have defined. I will show you an example of data model. For example, a device. My screen. Basically, it's why. Basically, it's what it is sent typically when we are updating all the attributes of device entity. For us, a device entity in this case is urban box. Urban box, it is a box composed by different sensors made by Ibatec, which collect different information not only on the environment, but also some information more generic, like the battery level of the box itself. We have the control property, which is the main measurement, the soil moisture. Basically, an urban box is put in a flower bed, so in the soil, and measure the soil moisture and determine then we need to water the flower bed, which is particularly useful in summer. And we have the location of the box. So we can use this location when watering. We know where the watering truck would go to water the flower bed. We have the name, owner, RSSI for the water for the wireless network, serial number, and so on. And also the value, which is the current value of the soil moisture measurement. Basically, it's a typical example of a patch request we should send to Orion Contest broker. Typically, we can do this kind of measure all hours, for example, 40 minutes, and so on. Basically, what we can do is to do a curl request. Here I have different examples. As we are running a little of time, I will show one example, but I have an example for each kind of data model used by Carouge. The first data model is the device data model, which is mapping, in fact, a sensor, any kind of sensor. Then we have a flower bed, representation of a flower bed, notably the location, which encompass all the information. We have the water quality observed, which is used to monitor the quality of water in a fountain. The water quality forecast to do some prediction on the water quality. We have the weather observed, which is monitoring the air temperature typically, and the weather forecast, of course. So a curl request is composed. The curl request is composed by a HTTP patch. We need to have always a content type, application JSON, the URL with the entity name, and I have put here the link to the file I have shown previously. Basically, I can copy paste this line, put inside a Linux console, and it will connect, and you see I will receive something which is okay. And if you look to this link, you can go directly to a web browser and you can find the entity updated. For example, if I go here, you can see the entity with all the value. And all is automated, and when something is wrong, we will receive a message error. So, I will let Matthew take again the token for the rest of the demo session.
Okay, thank you, Cédric. And we are coming slowly to the end of the second session. The last presenter is Kathy Schleidt, and she'll be demonstrating the OGS SensorThings API in this. Hello, Katie.
Hello, if you give me screen sharing, I can start.
Yeah. I made you a presenter right now. Yeah, floor is yours.
Okay, I still can't share. Okay, no, now I've got it. Sorry. Quick question, how much time do I have?
15 minutes is dedicated time. Okay.
Okay, I will do my best. Okay, I'm going to start out at the end, a nice user interface where we have our map. You can see everything. This is the water quality data from Baden-Württemberg. Right now, we only have the rivers displayed. First thing we have to do is add all of the stations for Baden-Württemberg. And that's where we also start seeing what SensorThings is doing. So down here, you already start seeing the requests. Let me zoom you all to a station we know is fairly good. Let me see if I can find the bugger here. This one is my special friend. Now we see what various properties does it provide. These are all the various different pollutants which are being measured at this station. Let us look at the Ca calcium, I'm assuming. And here we've got a time series. And how did that time series appear? So we go down here to the bottom and we find, we take this cool little request and we post it up into our browser. And we see, wow, we've got a nice little SensorThings request, which gives us for that one data stream, that point, a time series of all the values. In this case, we have it formatted as a data array because it's the easiest way for normal users to use this. So, I mean, this is the really tricky bit. And now let's go back to the basics. I'd like to start with just looking at this one data stream. So we pull this, the base part of the URL. I think Hylke has explained to you the basics. And let me go back to the basic, give you the very basic slide. If you look at the base landing page of SensorThings, you've got your base page, you've got the various object types listed there. You can say, okay, give me all data streams. Click on that link, you get all data streams. We don't want all data streams. Let's go to the one data stream we were looking at earlier, since we know this one has data. We copy the number from the end, and we put it at the end of the data streams. And now we have exactly this data stream. At the same time, I'd really like to start with my location. So I'd like to see what is the thing attached to this. So I go from that data stream URL, I add thing to the path, and suddenly we are at that thing. So I'm going to say this thing is now going to be my starting point. Let us go to the self link of that thing and start building a request up from there. So if you look at all of the object types we always have their IoT self links. So no matter what context you've moved into this object via, you find the self link and you find the object itself. The only caveat is for some reason Firefox eats the final parentheses. So now we have exactly this one thing. What can we do with this thing? So I mean, the first thing we could do is try and expand it again to the data streams we have attached to it. So Hylke has shown you the various different requests we have for playing with the SensorThings API. Let me also quickly show you the overview of tailoring responses. We have all of these nice little requests where we can nicely configure what are you really getting back from your API. So right now I'm playing with expand. That's the one where you can say, give me one class, but also give me the related class. So if we here at the end, we say we want to expand it to data streams. Now we have our thing. And here under data streams, you see we've got this long list of data streams with the unimaginably long list of observable properties. As has been mentioned fairly often here, water is tricky. We have all these different things which are being measured all at one station. If it makes you feel better, it doesn't get any better when you move off into air or into soil or any other of these environmental media. The same thing holds true. It stays complicated. Okay, we've expanded it to the data streams, but this is still a bit of a holy mess. So the first thing I'd like to do is chop this data down. We don't need all of the little details here. So the first thing I'd like to do is in the thing, I'd like to remove everything except for the name. So what do? Up here at the very top of the path, we add select name. And if all has gone well, has it gone well? Let me see. Yes, because here we've got the name of the station, and then we've got all of the data streams. So that worked nicely. And going into the details of the data stream, one thing I've been seriously missing here is that none of the presentations I've seen have actually given you the unit of measurement. What is the number? So, I mean, we aren't at the number yet, but we know the type of number. We know we've got whatever the pp ddt near Karlsruhe is. We'll get more detail on that in a moment. But we do know the number coming back is micrograms per liter. Further bits we can do here. Now I'd like to take the data streams down. We've seen the unit of measurement. We know that it's micrograms per cubic meter. So now we can ignore it and say for the data streams, we also just want the name. So we've got a very nice compact view here. We know this station has these, I don't know how many data streams. Okay, it's more than 100. I'm not going to page through those. But we know all of these different things are being measured at that station. However, we also want to get the observations off of these. So to do that, where we've got the select name at the end, what we can also do is we can add and expand observations. So let me slip that into the end. And now if you look, we've got things. We take the name of the thing, then we expand it to its related data stream. We take the name of the data stream and we expand it to the related observations. Here it's going to get a bit boring because we will find out that most of our data streams, this one actually has observations. Cool. So here we've got various results. The unit of measurement, we could have gone back. If I'd left that in the data stream, we would have it. Right now we just have the value. What else can we do? So, I mean, now we've got all of the values. And what if we only want the last value? To do that, we can again, now I've made a mess in my preparation. Give me 1 second. Here I've expanded the observations. Right now I'm providing them all. If I only want the last one, there's a nice trick that I order them by descending time, and then I only take one. So if I add that to the end, now if we look in here, if we go into we have our thing, we have our data streams, we have the observations on the data stream, we only have one. Sorry, that is 2016. I didn't have the time to find really current observations on this water system. For air quality, we have it in real time. Water is a bit more difficult. Okay, so we've got a nice way of paring it down. We have one station, we have all of the data streams, and we have one value per data stream. Really nice would be if we now take this down and say we want this for all things. So, I mean, if we do that, we are going to end up again with a holy mess. If I take the identifier of the original thing we're playing without, it's going to take a while. And now we find out we get all of these things without data streams because it turns out that, well, a lot of our things are actually rivers. And how can we get rid of all of the river bits? Okay, we've got to start filtering. So we want to filter things where we only want the things where the location is of type point. So if we put that filter in up to the very start, and we don't forget to put the little ampersand in, I think we've got a good chance of this request providing something. And we're seeing, I mean, it looks good. If it takes longer, it means that it's thinking. Mistakes, you get an answer quickly. Bingo. So we now have that filtered down, and we only have the ones which are points and therefore have data streams. Not all data streams have observations. Okay, that's already pretty cool, but how can we make this even cooler? I'm not going to jump a few steps ahead in the name of brevity. And I'm going to pare this down a bit more, and I'm also going to start adding some bits. So wait, look, I need to do one more check on this. So I've now done a fairly complex request. I've added location data. I've filtered it down that we're only now getting the parameter for the dissolved calcium. And now we get this holy mess. So we have our thing somewhere. What else do we have? We've got the name of the thing. We then have the location. So it's a point location. We've got the coordinates of that. We have the data stream, which is the dissolved calcium, and we have the last observation. And now we're off to the next thing, and that continues down. So for all of the stations which provide dissolved calcium, we have the last observation. The problem is if you now want to display this, I mean, it's all JSON. One can state that JSON is a standard. I see it more as a serialization option. Most tools I provide this with will have issues displaying this. Most tools I provide this to would really like something which is GeoJSON. And how can I do that to make people's lives easier? I go to the bitter end of the string, and I tell it, I'd like GeoJSON, please. And then I've got it nicely flattened. I do get some slightly funky property names. If you look at these property names, they're basically the concatenation of the path through the model graph. But if you can cope with that, you end up with nice little GeoJSON features. Here they've got their geometry, and they've got their name, and we know what they're providing, and we've got a result value. I can expand it and provide the unit of measurement. I can also expand it to provide information on the sensor utilized for doing these measurements. So, I mean, there's all sorts of additional information. I know that most users really just want the geometry and number to put on the map. That's fine if you're doing a quick mapping application. The moment you talk to the domain experts, they start asking these tricky questions of what is the unit, how did you measure it, all sorts of additional information. If you don't have that, they just turn around and walk because they say you've got numbers, you don't have data. So that's why SensorThings has all of these bits attached. That's why we've developed all of this in the observations, measurements, and sampling standard. And that's why there's also been formalized as ISO 19115. It could make sense to take a look at that standard and see to what extent it can be abstracted to FIWARE. To finalize this demonstration, I'd like to give you a few links for nice pages which explain what I've been doing. So here we've got a first page on the basic OGC API, SensorThings stuff, data model, and the like. If I can find the chat here, I can start giving you links. So there you've got a link for that base page. And then you've got a nice page on tailoring responses, all of the various tricky bits I've been doing now. So you can get that all then with the internal navigation. There are lots of further other cool pages there. Everything you ever wanted to know about SensorThings API is available there. And if you want to play with data sources, look up at the data nests. There we have for air quality, we've got for smart sensors, we've got the Franco-Germanic flow is the stuff Hylke and I have been mostly presenting. And we also, under the ad hoc sources, you see some nice additional things. We've added European air quality. So if you go to this, you've got real-time air quality up to the last hour for all European stations. Then we got silly. We started providing COVID values of how many people are sick, vaccinated, whatever. And then we realized there, actually, all of these numbers didn't make sense. This was before you had the number of cases per 100,000 over the last 7 days. We said we need the population to get a feel for what is the number of cases. And we ended up importing the demography from Eurostat. So we also have a SensorThings API endpoint that gives you demography values across all of Europe. Okay, that's it for the moment.
Okay, thank you, Hetty. Can you hear me?
Yes.
Okay. So let's then switch to the last part of our webinar. This is the discussion panel. I haven't received any questions into the chat, so yeah, please feel free involve even for the presenters. So yeah, it's now is the time if you would like to enter into discussion. But let me start with the first question. I will for Julian. A part that I have taken from your presentation is that there is never such a thing as a perfect data model, you said. And actually what arises from this statement is the question what it actually means from the standardization viewpoint.
It's an evil question, but I try to answer it as good as I can. Basically, every time you gather data, it depends on how you want to use it. So yeah, we saw a lot of the presentations. A simple example, I think, from what Hylke said and Kati also described a little bit, when I go, for example, to temperature measurements, I can do them in degrees Celsius, I can do them in degree Kelvin, I can do them in Fahrenheit. And yes, it's a very, very simplified example, but depending on where I am, it's better to use one or the other measurement for the temperature. While we, as Europeans, we mostly use degrees Celsius and sometimes degree Kelvin, and Fahrenheit is something strange for us. When in other countries, you do it differently. And I think the same. And yeah, this is basically the reason why we have such different things. Also, if I talk to a computer scientist, they want other data models than, for example, a geologist, hydroecologist, stuff like that, because everyone needs different points of the data. So, of course, they will model it a little bit differently. Regarding the second part, okay, how do we address it from a standardization point of view? We have several approaches. One we did in the Naiades project was, for example, that we tried to make, let's say, bigger data models, which have a lot of optional features. So, for example, when we have a sensor which could measure 10 to 20 different things, of those 5 are always interesting for at least one of the expert or one of the consumer of the data, we make this optional. So we know, okay, in this data model, there can be something from 5 to 20 different measurement parameters, like yeah, the temperature in degree, some pH value with some definition behind that. So we let it all away. This could be an option, or otherwise, well, you just have to see where you define it. So one step further would be that we define the data or in the data models where we define what is in the data model actually. So for example, the linked data we talked about or JSON-LD, that we can have some central repository where we say, okay, in this data model, we need that but a parameter. And if I want to do something differently, I can then have a different repository and link to that and say, okay, and in this case, I mean for temperature, something else. So this could be an option, but yeah, it's a difficult question because every time you want to design a data model, someone says, well, this is nice, but mine is better, for me at least. So yeah, sorry. You can't give you a good answer which fulfills all.
I mean, I can even turn around this question, and perhaps this is a question that I would like to ask Katie. And I was supposed to understand the difference between OGC SensorThings API and FIWARE from the presentation, but I still have a question. It's basically why do we have two standardizations? I mean, it's
what do you mean by two standardizations?
Yeah, I mean, I would prefer to have one data model, one way of encoding data for the machines to communicate between themselves, and not multiple standards. It seems that, I mean, FIWARE it's encoding data differently than OG SensorThings API. No.
Okay, I mean, I admit I'm not really up to date on what FIWARE is doing. I was involved 10 years ago. I haven't been involved since. All I can say from my side, I mean, OGC is an international organization that works around the world. It's the organization that creates the spatial standards for ISO. And why FIWARE has bypassed this is beyond me.
Okay.
That just a small answer, because Hylke laughs already, because I asked him this, I think 2 or 3 weeks ago. Basically, while they are different, because FIWARE is coming a lot from the smart city development, at least when I read in the development of it, and so they have some special formats. They didn't needed the spatial data as much in the beginning, so had early on only GeoJSON, stuff like that. Now it seems like, hey, there's more stuff which is interesting, like the EPANET. I think there's some on the smart data models, stuff like that. So they're looking into new stuff. But from the structure, at least from what I understood it and what I started to discuss with Hylke, and then we had to go somewhere else, it can be compatible. So this does not mean that we have two different standards which can't work together, but they could be combined. But we don't know how to do it the best way.
Well, I mean, question to you: Have you taken a look at the O&M data model? Because that is a very abstract conceptual model which can be applied to any context. I mean, SensorThings is using a derivation of it. Within the OGC, we originally had parallel to the web map service, web feature service, many people are probably familiar with. We also have the sensor observation service. That is still in the old school web services XML encoding. That is very, very tightly coupled with the O&M model. When then Steve Liang created the SensorThings API standard, he took the O&M model and he did a bit of semantic transformation. So he adjusted it to better support moving sensors, moving features, but it's still totally compatible in the background. So it's derived from the conceptual model. And what I was missing already when I was involved in FIWARE 10 years ago was going out and seeing what is available as building blocks from such existing standards and applying them. And a further bit of information, I mean, one of the things Hylke and I have been busy doing the last actually years by now is the OGC and ISO models have been updated. The final ISO DIS version was sent out a few days ago. There we've abstracted it even more. That the original O&M model already started with OGC feature types. I could see that if you're not willing to abstract to a certain degree, that could be a difficulty. That's the reason why in the updated version, we actually started with the top tier of the model is a conceptual model only defined as interfaces. We then break that down towards OGC features, going more into this ISO school of standards and concepts. But at the conceptual level, I'm pretty sure you can support those interfaces. And the advantage for you is, I mean, the bits where Hylke and I have been bitching a bit of where is the unit of measurement, what method was used for measuring the data. That was new to me when I started with observational data 20 years ago, that I thought I have temperature and I've got a number and I know it's in Celsius, what's the problem? And domain experts would look at me like I'm from the moon and say, I mean, you've got a number. What is that number? What did you measure that with? And the advantage of O&M is that you have, I don't know how many people from around the world. The standard started around 2000, was abstracted from GeoSciML. became a first OGC standard sometime around 10, 15 years ago. And we've been building on it since. And you've got the brains of the world who have gone through this and made the mistakes and realized, whoops, we forgot that, we have to add that. It's all there. It's a nice toy box where you can sit down and see what do you really need, what have the various experts around the world realized, whoops, we shouldn't forget that.
So okay, if I a little simplify, you're basically saying that one of the differences between FIWARE and OGC SensorThings, it's that, for example, OGC SensorThings can provide information about the method of how some unit has been measured, while the FIWARE can't.
Yes, the SensorThings API can supply. Well, of course, SensorThings API can only supply what you put in. So if you don't put it in, it can't supply it. But you do have a nice framework in the form of the O&M model for all the things that are important when you're looking at observations. So it's easier to not forget things when you do put them in. And you actually see quite a lot of cities that have standardized on FIWARE that are now also starting to add SensorThings API to their services, because it's simply very convenient for querying your data, and also for end users. It's a very easy way to get the data that they need.
So this is as concerns the API probably, no, but not the data encoding.
It's a combination, because the API is based, of course, is the SensorThings API itself wouldn't be much without a data model behind it. So
yeah,
an API is always exposing a data model.
Okay. Yeah. Okay. So, for example, if Wolfgang, if I ask you very concretely, because I've seen that you've based your work on FIWARE. Why have you chosen FIWARE, and why haven't you chosen OGC SensorThings? And actually, this question goes also to Cédric, because the same as within Naiades, the FIWARE was preferred over the why one over the other.
Yeah. Maybe I'm not the best person. So I'm from education. I'm an environmental engineer. So before I started this project, I actually did not know that FIWARE existed, and also I did not know the difference between FIWARE and API SensorThings. So maybe this was not a choice I made personally, but which was more or less a set boundary condition in this case.
Okay, thank you. Cédric?
FIWARE does have the advantage that there's a lot of push from the European Union and a lot of money available.
Yeah, and from a very practical, maybe just from a very practical point of view, so in Berlin, we made the experience that, for example, the Berlin water utilities, which have a lot of data by their own, they usually do not allow data to be directly requested from their system because of security issues. And what I found then when I used the context broker, I found the use of the context broker very convenient, because it solved actually this problem that the data owners can actually simply post the data to the context broker, where I can collect them without having to access their system directly. But yeah, this was just my personal view.
That would be the same if you use SensorThings API, because in the SensorThings API, the data owner also has to push it to a SensorThings API service, unless the data owner wants to make it available themselves, which is, of course, also possible. Often not.
I mean, one advantage of SensorThings API, I mean, all of this is happening in the European context. Most of this data actually falls under Inspire. So it has to be made available by the various data owners via the various mechanisms laid down by Inspire. one of the cool things is we've gotten SensorThings API now certified as an Inspire download service. So if Berlin is exposing it with FIWARE, they still have to do a separate endpoint using either SensorThings or Sensor Observation Service to fulfill that requirement. If they utilize SensorThings, they have it all covered.
So perhaps before Cédric starts, or if you want, because I thought you wanted to say something again, or before me.
Basically, what I mean, you are right. FIWARE is very well known in Europe because all the IoT programs, projects are using this framework now. Not only in the concept of smart water, but smart cities. And there is a lot of things we can reuse freely, quickly. And at the end, this FIWARE components can be reused, and everybody can use it across Europe and the world. So it avoids to reinvent the wheel each time a new project is starting, in fact. Also.
Perhaps because what Cédric said was one of the reasons why we used it in Naiades, because I think this would be your next question, is for us was not only the data model and the exchange format for the SensorThings API, which can be nice for querying, stuff like that, because we're looking into it in other projects as well. So we're not against it, but we are looking at it in both ways. But for Naiades, what was quite the tempting offer from FIWARE was, apart from data models, what we focus on today, is it's a whole ecosystem we could use. So we saw about the Orion Context Broker, we saw the historical database, a lot of the stuff which is in FIWARE was for us quite nice, because then we had a full package we could use. And I think, as most of us said before, since it's an EU project and we're funded by the European Union, and a lot of other projects also use FIWARE, it's nice to be FIWARE compliant, use similar data models so we can exchange the data, can exchange the experience easily between other EU projects. So this was one of the reasons why we focused on FIWARE during the project. Also, for our use case and what our use case partners needed was that the possibilities of FIWARE in regard to the spatial data were just enough. So everything which goes beyond what FIWARE could do 2.5 years ago now, when we made the decision to use FIWARE, was exactly that what our use case partners needed. So everything which goes beyond, like the raster data from GIS, stuff like that, which we could use like GeoServer and things like that, we don't need it at that moment, and were not expected that the use case partner needed it. So we didn't look as deep into the spatial data formats. Nowadays, or when we look perhaps as a Naiades 2, one can hope, I would look more into other data formats and tools to then combine it with FIWARE, because I think that could be a nice extension. But well, let's see if this comes to fruition.
Yeah, one interesting thing I just noticed today is that ICCS is one of the partners in Naiades. They actually have a SensorThings API service registered at OTC website. So they made an implementation too.
Okay, yeah, we don't have anyone from ACCS, no, probably, no. Okay, so let's get a little more specific in terms of FIWARE system. Cédric, when the Naiades has adopted FIWARE, in your opinion, how ready was the FIWARE to be applied within Naiades? And have you encountered many chasms between, let's say, some theoretically designed data models and the practical application?
Basically, at the start of the project, we have started by using FIWARE NGSC version 2, which was, I think, the better one at the time of the starting of the project. And in parallel, FIWARE has started to develop NGSCLD, which is more appropriate for the goals, final objectives of Naiades with semantic interoperability and the use of machine learning and artificial intelligence. So now we are working to update the IoT platform to NGSCLD. And in terms of data model, we have seen at the beginning of the project some missing things, which we have decided to improve, to complete the data models for the water sector, in fact.
So it means that FIWARE it's like making these major updates. It's developing pretty fast, because it means that within the 2 years' time you had to switch from one to another definition, and did that has this resulted in many problems within the project, or it was?
Basically, we have tried to resolve all the problems by doing something which is hybrid, in the sense we can use NGSC version 2 and NGSC LD. Thanks to FIWARE developments, we can have an hybrid approach, because NGSC LD components are supporting also NGSC version 2. So it's a bigger problem in terms of compatibility.
Okay, so for example, compared to OGSC SensorThings, I mean, is it also evolving so fastly, and or this evolution phase is already behind its more stable system? This is for Katie or for Hylke, the question.
Sorry, I couldn't hear the question very well. Can you repeat that?
So, for example, within Naiades, in the past 2 years, the FIWARE really evolved in some aspects. The question is whether SensorThings is more stable in this development evolution of its system, or it's also changing, fastly evolving and then changing. And I mean, compared to Naiades, what's the situation in OGS SensorThings?
OGC. The version 1 of SensorThings was released in 2016, and this year we released version 1.1, which is almost completely backward compatible. So you don't really need to change your queries if you're using 1.0 or 1.1. And we're currently looking into version 2, and how backwards compatible that will be, we'll have to see. But I think the data model will not change much. A little bit probably because the data model, the O&M data model, was updated a bit. But I don't expect big breaking changes. Mostly new additions.
Okay, thanks. So now a question for Kathy. So one thing I would like to also know and understand is the European policy towards the data models, and how, for example, what is the European policy context in terms of this SensorThings APIs and FIWARE and all these IoT frameworks being developed?
Okay, I mean, FIWARE I cannot speak for, because that is not my area. What I can say, I've been working for the last, I don't know, 12 years towards the European Inspire Directive. I'm not sure who here is familiar with that. That's a directive. It hits more the administrative organizations, as less a topic in the research area, but all European administrations have to provide all spatial data they have for a set of 34 different spatial data themes, and this has to be made available online by standardized data models following the various ISO standards which came out of OGC. We have data models for all of that, we have service specifications for all of that, and all European member states are putting this data online. The process is a bit behind, but that's usual. And as stated a bit earlier, it used to be that for providing this type of measurement data within the Inspire constraints, you had to use the sensor observation service. That was admittedly a bit difficult and clunky. And one of the things Hylke and I worked on the last years was getting the SensorThings API accepted for Inspire. So in that policy context, the requirement for all of the administrative organizations across Europe who are obligated to provide all of this measurement data as real time as they can. That's also under the Access to Environmental Information Act in Europe. So I mean, there they have to provide it anyway. I've forgotten what I think is now the Open Data Directive. So that's requiring more a proactive providing it. So I mean, it's long been so that if you want some environmental data from some organization, I could go to the Swedish Environmental Agency and say, give me your water quality data, and they have to give it to me in 4 weeks. Or say, why are the data privacy concerns? Now it should be made available proactively online via web services, and SensorThings is the web service which has been accepted there, or API. So I have no idea what FIWARE is planning in this regard. From what I've seen, it's been mostly focused on the research end, plays a bit in smart cities, where again in smart cities, we've also had some very good experience with SensorThings. As Hylke has mentioned, various cities are now shifting to SensorThings. And it's partially that it makes their lives easier. I mean, the city of Hamburg has to provide the data to Inspire and to other things. If they use SensorThings, they do it once and they're done.
Okay, thanks. If I now come to my last question, it's obviously EU tries to encourage the data sharing, the open standardization, but then again, from one of the presentations, it's been said that there is no an agreed exchange format, which is very convenient for the private entities to make a vendor lock-in. What is, for example, the situation? So overall in Europe, I mean, what is, for example, how these open standards are dominant over the private standards, or vice versa? I'm not sure who to ask, but that's, for example. Or Julian, perhaps?
Can you repeat? I tried to understand it. I have not yet understood how to answer it. Sorry.
The question is, there's basically a button between the companies and the open standards, where the companies through their private standards can execute a vendor lock-in, and the open standards, on the other hand, they're trying to make this machine communication universal and open. And what's the status now in Europe? I mean, are the open standards prevailing, or it's the capital behind the private entities, pushing it on their side?
As always, it highly depends. That's the standard answer I'm going to give. Here it's the OGC is a nice example here, because that's something most companies use. Because, well, a lot of geodata is historically publicly created. So therefore, since all use it, well, then also all the big companies use it, because that's the standard they use. For other things, it's difficult to say. We see in the FIWARE context that a lot of, especially SMEs, so small to medium enterprises, are using the new standards, try to integrate there, because that allows them to have a bigger customer base. So that's a nice thing. But some of the really big companies, at least from my experience, and when I used to talk to some of the local municipalities here in Germany, well, they say, we are big, we can enforce what we want. And why should we adapt to standards? This still happens sometimes. So it's difficult to say if this will happen in the future, but I have at least hopes that most will adhere to most of the public standards. And for some, as told before with the Inspire standard, for example, since all the governments should adhere to it, or have to, basically, and some of them actually do, then it's easier to exchange the data in that format. When everyone will use it, then big companies also will adapt. I say should, because I live also in the state of Baden-Württemberg, and our provincial government has the good old reasoning: before I give any data point away for free, I will charge so much, because why should people use data to create something new? I think we're one of the most restrictive in the host country of Germany regarding that, which, well, sometimes is annoying when you're looking for additional data. But there's hope, so I have to be optimistic. I am actually optimistic.
So basically, it's not only the company's interest involved, but also the mentality and the attitude towards the data. And
I think it's also at the moment still it's always a bit of a fight between the users and the companies implementing products. And the whole IoT field is, of course, relatively new. So here the companies still have the advantage of being the first movers. If you have your Philips light bulb, then the only thing you can use to control it, to check it, to change the settings is using the Philips app. But if you then in another room have an Osram light bulb, then you also need the Osram app. And of course, users are not happy with that situation. And then when it comes to data exchange, and that's a situation where there's no real data exchange going on, because it's just a user controlling his own light bulbs. But then when you go to smart cities, then you suddenly have an organization, for instance, the city of Hamburg, that is exchanging data with the general public. And so the city of Hamburg had to basically choose, when they wanted to make their smart city data warehouse, what API are we going to use? And if they had chosen a non-open standard, they would have had to have some way to make the end user actually being able to get to the data. So they would have had to describe that API themselves, because it's not an open standard and there's probably not a good API description. So that's one of the good reasons there to choose an open standard. That's a lot easier, and then it doesn't really matter what open standard you use, as long as it fits your use cases. And of course, the second point then is also the city of Hamburg wanted to host it all on open source, so they're also not bound to a vendor. You do see that organizations have learned a lot from the past in avoiding vendor lock-in. So it's, but the companies, of course, keep trying to push their own things, and especially large companies like Google, and they like to build their own versions of APIs, regardless of what users want and need.
Okay, thank you. Thank you for the answers. Thank you for your presentations. Unless there's anyone who would like to ask an additional. Okay, there are two comments. I haven't. Okay, yeah, it's not a question.
Additionally, I posted in for people in case it's useful for somebody. They've got all of the Inspire data specifications, can get an overview of what I've been talking about. Okay, thank you. I would like to thank you all, and I'm concluding this webinar, and yeah, wish you a nice day and lots of open standards, and continue our work successfully, of course. Thank you very much.
Thanks for inviting us.
You're right. Goodbye.
Very happy
Thank you also.
Bye, everyone.
Bye. Bye.
Bye.
Goodbye. Thank you.
Bye. Thank you.